Today we're going to combine programming with basic Newtonian physics, and we're going to simulate as well as visualize planet orbits in Python. So let us get right into it. Alright, so this is going to be the perfect project for beginners to practice their programming skills. You should have some basic understanding of the Python programming language. You should be familiar with functions, classes, loops, if statements, variables, and so on. But besides that, you don't need to be an experienced programmer. The only new thing that you might not know about is PyGame, which is a package or a library for developing games. We're going to use it for animation mainly. And essentially there's two ways in which you can follow this tutorial. One is you try to implement the whole thing from scratch without watching the tutorial. And if you struggle or if you fail, you can watch the tutorial to see how I did it. I don't claim that my solution is the best solution. It's just a solution that works. You can compare and see why yours maybe doesn't work and mine does. And the second way to watch this tutorial is to just watch it from the beginning, to code along while watching, and to essentially copy the code, but typing it out yourself, and to understand every single line of code, what it does while you're typing it. So not just blindly copying every single line and just typing it, but understanding, okay, this line does this line does this. And in the end, you can either go and recode the whole thing from scratch without a tutorial, or you can try to extend the functionality to play around with the existing code, to add functionality, add animations or something like this, just to see if you can extend the functionality of the already existing program that you sort of copied from this tutorial here. So these are the two ways I would recommend for beginners. And now let us go ahead and set up the environment. I'm going to go to my tutorial directory. And in here, I'm going to use UV as my package manager. You don't have to be confused by that. You can just go ahead and say pip or pip3 install PyGame. That's the only thing that you're going to need in terms of external libraries in this video today. In my case here, since I'm using UV, most of the time I'm going to do UV init, UV add PyGame, and I'm going to use a virtual environment. You can also do that if you want to. I have a video on UV on this channel, so if you're interested in that, check it out. Otherwise, just use pip or pip3 or venv or virtual env. So once we have that, I'm going to go into the main py file. I'm going to delete all of the code here that is created by default. And here we're going to import now the two packages or the two libraries that we're going to need. One is math. This is a core Python package, which is for mathematical calculations like square root, for example. And then we're going to import PyGame, which is what we're going to use for the whole rendering and animation stuff. So let us next initialize the whole PyGame stuff. So we're going to say here pygame.init. Then we're going to set a width and a height for the screen. Let's go with the classic 800 and 600. Then we're going to say screen is equal to pygame.display.set mode, and we're going to pass a tuple of width and height. And then we're going to say pygame.display.set caption is going to be planet simulation, for example. So this is just going to be the title of the window. And what we also need for the whole thing to be updating all the time is we're going to say clock is equal to pygame time.clock. So this is what basically keeps the whole simulation running. And now the next thing that's important here is we are going to use Newtonian physics. Now, don't worry, this is not going to be super mathematical, or we're not going to go too deep into physics. We're going to just use two formulas from Newton, and we're going to use Newtonian physics because it's good enough to describe the motion of planets, at least for the purpose of this simulation here. Now, I'm not a physicist, so maybe I'm not the best source for this. I'm not the guy to trust here, but as far as I understand it, the general relativity is actually the correct way to analyze this or to simulate this, but Newtonian physics is good enough to not be a problem here. So it's essentially not true, but it's good enough to give us accurate results. So we're going to use Newton's formulas. And why I'm saying this is because now we need to define the gravitational constant. So that is a value that we're going to use for the calculation of velocity, acceleration, and so on. So I'm gonna type it in here. It's 6.67430 e minus 11. Now, what does e minus 11 mean? It means that we basically shift the comma to the left, so it becomes 0.000 and so on. 66743. So we shift the 0 11 places to the left, 11 times to the left. or not the 0, the decimal point here. So basically it becomes 0 point whatever, and then 66743. That is the gravitational constant. Then what we also need to do here in terms of PyGame is we need to decide the scale, because of course we're not going to have the actual sizes, and we're not going to have the actual values here displayed in PyGame in terms of the planet sizes and in terms of the sizes of the sun and so on, or the size of the sun. So we're going to have a scale on how this should be visualized, or maybe we could also call this a zoom level if we want. And we're going to start with a default of 6e minus 11. And then we're going to also say zoom scale, because I want to have the feature that when I press a certain button, in my case, I'm going to go with Z. If I press that button, I want to be able to zoom out and see all the planets, because I want to have a more detailed view where I see the sun and the earth and also Mercury and Venus. But then I want to also zoom out and see everything up until Pluto. So for this one, I'm going to say 1e minus 9. Sorry, the other way around. It's this one shows everything, and this one zooms in to see the Earth and the Sun in a closer way. Then we're going to define the time step of the simulation. We're going to have 1 day. So we're going to say 86,400. And these are now the constants that we're going to use for the simulation and also for the visualization of the simulation. Now, in addition to that, I also want to have a variable zoomed, which is going to start at false. So this is going to control whether we're zoomed in or not. And then we're going to go to the central class here, which is the body, the celestial body. And this is going to be a planet, a sun, whatever. We will have a position, we will have an initial velocity, we will have a mass, and we will have a radius or a size. But the size is not going to be relevant for the calculation. It's only going to be relevant for the visualization, so it doesn't really change anything in terms of behavior. And we're also not going to make it accurate, so we want to still be able to see the smaller planets. So I'm not going to actually show the size of the sun compared to the size of the Earth in a realistic way. I'm just going to symbolically make the sun a little bit larger, but it's not going to be accurate in terms of scale. So let us start with a constructor with the init method. We're going to have self, we're going to have x, y, we're going to have vx, vy. Basically, this means initial position and then initial velocity. Position meaning x coordinate, y coordinate, velocity meaning how fast is it going into x direction, how fast is it going into y direction. Then also, as I said, mass, then radius, which is just for the visualization, and color, which is also for the visualization. And then we're just going to set the values. Self.x is equal to x, self.y is equal to y. And then we're going to do the same thing here with vx, vy, like that. And then self.mass is equal to mass, self.radius is equal to radius, self.color is equal to color. Now, one more thing that we need is we need to keep track of a trail, or at least I want to do that. So I don't just want to have the point or the dot being moved. I'll also want to have like a trail behind it to see what the orbit looks like. So I'm going to say here self.trail is equal to an empty list. And here we're going to keep track of the path that the body is going through essentially. So that is our constructor. And now we're going to have the whole logic in the update position function. So that is going to be our physics simulation. We're going to have self here as a keyword, and then bodies. Bodies is going to be a list of celestial bodies in the same simulation, because of course the velocity and the change of velocity is going to be determined by other bodies because they have a certain mass, they attract our body, we attract them, and so on. So it's going to essentially be this play and this physics simulation essentially. We're going to start here with initial forces acting upon our body of 0. So basically force in x direction and force in y direction is going to be 0 by default. And then we're going to iterate over the other bodies. So for other in bodies, we're going to iterate over the list of bodies that we pass here as a parameter. And we're going to say if these other bodies, or if this other body is not the body itself. So if this is not the same here, because of course the bodies list will contain all the bodies, including this one. So if that is not the body itself. Then we're going to do the following calculation. First of all, the distance in x direction. So dx is going to be other.x minus self.x. Then, of course, we want to have the same in y direction. And then we also want to have the total distance, the Euclidean distance, so to say, which is going to be r. So math.sqrt, math.square root of dx to the power of 2 plus dy to the power of 2. So basically Pythagorean theorem here to get the actual distance. And then we say if the distance is not 0, or if it's greater than 0, then what we want to apply is Newton's formula for calculating the force between two bodies based on their masses. So F, the force, is going to be equal to the gravitational constant g times, and then we have here mass 1 times mass 2 divided by r squared. So like this, r squared. That is the formula. By doing that, we get the entire force. Then we can split it into x and y direction based on the distance. So we're going to say here force is equal, or maybe I should do capital, maybe capital F is not good. Let's do lowercase f, is equal to g times self dot mass times other dot mass divided by r to the power of 2. And now splitting that into x and y is quite simple. We just have to say fx, and then important here, plus equals, because we're not just setting it equal to that. We need to consider all the bodies, and because of that, we need to add all the forces together. Think of it to be a little bit like a back propagation or a gradient descent step in a neural network. You don't just want to go into the direction of one impulse for change. You want to consider all of them and then basically do the entire or consider the entire gradient that is the result of that. And in this case, here we want to consider all the forces before we actually do the change. So we say fx plus equals f times dx, so the distance on the x-axis divided by the distance r. So that is going to give us the force in x direction, and the same thing here with y is going to give us the force in y direction. That is basically it. And now what we need to do based on that, after this loop, after we've considered all the things, we need to apply Newton's famous formula, which is F is equal to ma. Force equals mass times acceleration. To be precise, we're going to say acceleration is equal to force divided by mass, because we want to have the acceleration. Ax is equal to, and now we do it, force in x direction divided by self dot mass. And for y, we do the same thing in y direction with the force y. And this is our acceleration. And then all we have to do is we need to update the velocity and we need to update the position. So the position is going to be updated based on the velocity. The velocity is going to be updated based on the acceleration. So we say self dot vx is plus equal, or vx plus equals ax times dt, which is our time step here. So a day, essentially. We do the same thing here with y. We do the same thing here with y. And then we say self dot x plus equals vx times dt. And then here again, y and y. And that's basically it for the physics calculation. We do need to do some calculation now in terms of the scaling and in terms of the trail. But besides that, everything else is going to happen in a separate function or method called draw. Like this, so I'm just going to pass for now. But we need to consider the scaling. So we're going to say current scaling is equal to zoom, or what was it? Zoom scale if zoomed else scale. I think these were the constants. Yes. And then we also need to keep track of the trail. So we're going to say here self.trail.append. Then int self.x times current scaling. Maybe I should call this current scale. Sounds better. Current scale, x times current scale plus width divided by 2. So floor divided by 2 to have an integer, obviously. And then int self.y times current scale plus height floor divided by 2 as well. So that is going to be the tuple that we add to the trail, and then we're going to say if length self.trail is greater than 200, we're going to remove the last entry. So we're going to say, or the first entry, so to say, the one that we added first. Because we don't want to keep track of the trail all the time and never delete it. We want to have only the most recent movements, so the last 200 movements. And here we're going to say pop 0, so pop the first entry, and yeah, basically continue like this. That is our logic. The next thing here is visualizing all of that. For this, we need to have a screen. We're going to pass the PyGame screen here, and it's essentially just turning this now into circles and lines. So if the length of self.trail is greater than 1, so if we have actually more than just a single point in the trail, what we're going to do is we're going to draw lines. We're going to say pygame.draw.lines, and we're going to draw it on the screen with a gray color, so 50, 50, 50, so that it's not too aggressive. We have a black background, so this is a dark gray, a somewhat dark gray, which is going to be our line. And then we're going to say here false, and we're going to say self.trail 1. So we're basically going to draw the lines based on the trail that we appended here. So based on the points. The trail is essentially a list of points, and we connect these points now with lines. That's essentially it. Quite simple. And now we need to do again, current scale is equal. Let me just copy this from up here. Current scale is equal to zoom scale of zoomed, otherwise scale. And now we need to say screen x is equal to int self x times current scale plus width floor divided by 2. Same for y, and self.y and height. So we're basically trying to figure out where the position is on the screen based on our coordinates here. And now we say pygame draw circle, and we represent our sun and our planets here as circles on the screen with a given color at the position screen x, screen y, with the size radius, which is just going to be symbolic. Again, it's not going to be an accurate scale here. That is our draw method. This is our update method. And the only thing left to do here now is to have bodies that we define. So we're going to actually create planets and the sun. And then we're going to actually have the main loop, which is going to do all the draw calls and so on. So we're going to say here bodies is equal to a list, and I'm going to define one here manually, and the rest I'm going to copy from my prepared code. So I'm going to say here body, which is going to be the sun in the beginning, is going to start at 0, 0 at the center of the screen with no velocity. So 0 velocity in x direction, 0 velocity in y direction. And it has a mass of, this is actually the mass of the sun, so 1.989 E30. So that means 30 zeros. Now, not 30 zeros in addition to 989, but moving the comma to the right 30 times, essentially. And the radius of that is going to be 8, and the color is going to be yellow, so 255, 255, 0. This is RGB, so red, green, blue. Red and green is yellow, so this is why we choose that. This is now the sun, and all I would have to do now is do the same thing for Earth, Mercury, Venus, and so on. And what I'm going to do instead is I'm going to just copy and paste them here from my prepared code. You're going to find the code in the description down below on my GitHub. And that is basically what we're doing here. Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune, and Pluto. These are the planets here in their respective positions. They all start just on the x-axis with no y value and with their respective masses. And I think this is, what is this? This is the initial velocity, I think. Yeah. And with the different colors and the respective radiuses. Or actually, I think radius has a different plural. Let me know in the comment section down below. All right. And the final thing that we want to do is we want to say now running equals true. While running, we're going to keep our simulation running for event in pygame.event.get. If something happens, if event.type is equal to pygame quit, And then we want to say running is equal to false. Also, as I said, I want to have the key for zoom. So if the event type is, come on, if the event type is equal to pygame.keyDown, then we want to say if event key, so the actual key that was pressed, if that is equal to pygame.k_z, in my case, then I'm going to say zoomed is equal to not zoomed. So just flipping that, toggling that, so to say. And also I want to get rid of the trails because the trails are not going to be accurate in terms of the zoom, I think. Not sure about that. So I'm just going to say for body in bodies, body.trail is equal to an empty list. So we just reset every time we zoom in or out. And then we're going to say screen.fill, fill it with black color, so 0, 0, 0. And then for body in bodies, we want to update the calculation. So body.update position based on all the other bodies. And then we want to say draw the individual bodies. So body.draw. And finally, we say pygame.display.flip and clock tick 60. And in the end, Pygame quit. That is the code. As always, probably I made some mistakes somewhere. So let me add a comment here that this is actually f is equal to ma as a basis here. And let's see if that works. So what I'm going to do now, since I'm using UV, is I'm going to say UV run. In your case, if you're just using ordinary Python with pip, you say Python or Python 3 main.py. In my case, this is not going to work because I don't have PyGame installed on my system. So UV run main.py. And we have a problem. Did you mean fx, not vx? Yes, of course. Vx doesn't exist because it has to be self.vx. And this is here, self.vx, self.vy. And we also have a problem with screen. I didn't pass the screen. So let's do that. And there you go. So now we have a very slow orbit here for all the planets, as you can see. But if I press the Z key, you can see here Mercury, Venus, and Earth. We don't have the moon here. 3-body problem. I don't think this is going to be very useful if I add the moon here. But you can see the orbit here close up. If I press Z again, you can see how the other planets are slowly moving. Yeah. Of course, you can also speed up the simulation, but that is basically how we can simulate and visualize planet orbits in Python. And your job right now is to either code this from scratch, so to re-implement this without a tutorial, or to extend it in terms of functionality. Add some random bodies, try to mess stuff up. So for example, let me just copy paste a bunch of random bodies here that I prepared. I mean, not prepared in terms of they're super fancy, just some random values here that I generated with AI. Basically, if I run this, you will see, of course, I can run it like this. There you go. You can see it messes stuff up quite a bit. So you can see what happens here is very chaotic. You can play around with that, and you can also, of course, add more visualization, more key controls. Maybe if you press a button, you want to spawn a new planet or something, or when you press with your mouse somewhere on the screen, maybe you want to do you want to place a new planet there. This could be an interesting feature. Play around with this and make sure you understand the code. So that's it for today's video. I hope you enjoyed it and hope you learned something. If so, let me know by hitting a like button and leaving a comment in the comment section down below. And of course, don't forget to subscribe to this channel and hit the notification bell to not miss a single future video for free. Other than that, thank you much for watching. See you in the next video, and bye.